To define our potential energy, what we will say is that the work in going from point 1 to point 2 by our external force, which we've already seen is the integral from 1 to 2 of F dot dr, that will be equal to the potential energy at point 1 minus the potential energy at point 2. Now, does this make sense with gravity, say? Well, if we think about the skier going down the incline from point 1 to point 2, what we have is the work done by gravity. So in going down, the work is going to be positive. In other words, we're going from a point of higher potential energy to a point of lower potential energy. And as we would see, the potential energy at point 1 is going to be greater than the potential energy at point 2, because the point at point 1 is at a higher elevation than point 2. So that's going to be a positive work, and when U1 is greater than U2, that will be a positive number. So a positive work, a positive change in the potential energy here. Well, it's not really the change. It's not final minus initial, but it's the initial minus final in this case, because the initial potential energy up high will be larger than the final potential energy down low when the force is actually doing a positive work in going from 1 to 2. Okay, well that's great. So what can we say about this? Well, the change in the potential energy, in other words, the final minus initial, U2 minus U1, reverse these, will then be the negative of the work in going from, I switched these around. The negative of the work in going from point 1 to point 2. Point 1 to point 2. Okay, very, very good. Now, I want to put in one little point here. If there is a place where we can define the potential as 0, so if there is some point where our potential energy can be set to 0, I'll call this U0 equals 0. If there's some place where we can do that, then what we can actually say is, rather than just defining differences in the potential by this work, we can actually define what the value is at some point. What we do is we can say that the potential energy at point 1 will be the negative integral from this point 0, from point 0 to point 1 of F dot dr, and then the potential at point 2, or whatever, any point, will be negative, equal to negative the integral from this 0 point, wherever this potential is 0. Gravity, wherever the height is 0, or the spring, wherever the potential is 0 for that. So we're integrating from this position where the potential is 0 to our final position where we're trying to determine the potential, U2, of F dot dr. Now, how does this work? Let's see, how does this fit in with our definition up here? Well, let's take U2 minus U1 and see what we get. If we take U2 minus U1, that will be negative integral from 0 to 2 of F dot dr minus U1, which is negative the integral from 0 to 1 of F dot dr. Let's pull a minus sign out, and what do we get? We get minus the integral from 0 to 2 of F dot dr. Pull one of these minus signs out, and we'll have minus the integral from 0 to 1 of F dot dr. Okay? And then we've got minus the integral from 0 to 1. I'm going to change this to a positive and just switch the order of the integral. So I'm going to make this plus, and then integral from, rather than 0 to 1, 1 to 0. 1 to 0. Okay? There we go. Now, let's look at this. What do we have? We've got an integral from 0 to 2 and an integral from 1 to 0. So if we've got point 1 here and point 2 here and some point 0 over here, this is an integral from 1 to 0. And then this is an integral from 0 to 2. So what are we really doing? We're going from 1 to 0 to 2. In other words, we're going from 1 to 2. But if the pathway is arbitrary, then this is going to be equal to any integral from 1 to 2. So we can replace this as negative integral from 1 to 2 of f dot dr, and that is exactly what we had up here. So that is exactly u2 minus, that's negative of this, which would be u2 minus u1. And there we go. That's exactly what we got. That is delta u. Here. There we go. So what's the point here? Well, the point is that if we choose some place where we want to set our potential equal to 0, we can choose any arbitrary place where we want to set our 0 potential, and then we can define our potentials at any other place, point 1 or point 2, by just doing the integral from that place where the potential is 0. But that's exactly what we did for gravity and the spring constant. Where did we set u equal to 0 for gravity? That was where y was equal to 0, our 0 height. We arbitrarily chose our 0 height. Where was u equal to 0 for the spring constant? For the spring potential energy, sorry. For the spring potential energy. Remember, for the spring, we ended up with u was equal to 1/2 kx squared. Well, where is that 0? That's 0 when x is equal to 0. In other words, at the equilibrium value. The equilibrium of the spring, wherever the spring would come to rest when there's where the spring is exerting no force on the mass. We can put it that way for a horizontal spring, for example. So it's arbitrary. We can choose any point we want and set our potential to be 0 there, and then any other points can have their potentials defined in terms of the integrals from that 0 point. Okay, that's a very powerful result that we'll use again later on. Well, what this has done is allowed us to go from a force, from some defined force, and figure out what the potential is at any arbitrary point. Can we go the other way around? If we had a potential, could we use that potential to determine the force? Actually, yes, we could, and it's really not that hard. Starting with this new definition for potential energy, u is equal to negative of the integral from some starting point, 0, some arbitrary 0 point where typically we think of the potential as 0, but it doesn't actually have to be 0, just any arbitrary point that we want to set, from 0 to our final point r of f dot dr. Let's look at this in just one dimension, just to make it a little bit easier for us, just for a minute. Let's just imagine this is then the negative integral from 0 to some final point along the x-axis of f dot dx, and then f dot dx will be f sub x, the x component of the force, dx, integrated from 0 to x. Well, if we think about this, this is telling us, with the negative sign, the little infinitesimal change of the potential as we integrate. In other words, the little changes of u will be negative of f sub x dx. And what we're doing is we're integrating all of the little infinitesimal changes to give us the total change in u. But right from here, bring the negative and the dx over, fx equals negative du over dx. And that tells us what the force is in terms of the potential. All we have to do to figure out what the force is, if we know what the potential energy is just differentiate. If it's a one-dimensional problem, just du dx, put in a minus sign, and that tells us what the force is. How does that correspond to what we've already done? Well, let's just take a look at the two potentials that we know about, the gravitational potential and the spring potential. What is the gravitational potential energy? Well, it's mg y. Well, we were talking about the vertical axis as y. Let's just write this then as f sub y is negative du dy, and see what we get. Well, if we differentiate this with respect to y, du dy is mg, which means the force in the y direction will be negative mg. Well, that is exactly right. That's just the negative of the weight in the negative y direction, defining upward as positive, that gives us a weight in the negative direction, downward. But that's exactly what we had before. That's what one of the first forces we were looking at, the gravitational force. It's just the weight acting downward. Well, that's perfect. Okay, what about the spring force? What about that one? We determined that the potential energy was 1/2 kx squared. What is du dx? That would be differentiating x squared. That's 2x. The 2 cancels a half. We have kx. The force is then the negative of that, minus kx, and there we go, Hooke's law. Perfect. Very, very good. This seems to work perfectly. Okay, great. Let's take a look at the shape of this potential and see what that can tell us about the motion. The spring potential energy has the form of 1/2 kx squared. If we were to graph this as a function of x, it's just going to be a nice symmetric parabola. Now let's imagine, or let's try and figure out what the motion looks like. If we have an object moving in the x-axis, in other words, on the spring. So imagine here's the spring like this, and here's our object. When we move the object to the right, the spring force is back to the left. So over here, the force is negative. Well, and remember that makes sense. In terms of the force being the negative derivative of the potential, here we have positive derivatives, which are going to give us negative forces. When we push the mass over here, we know the force is going to be back to the right. In other words, the force is positive, and that makes sense. Over here we have negative slopes, and the opposite of that will be a positive force. So we can think of this almost like the object is inside a bowl, and when it's on the right side of the bowl, the force is pushing it back down. When it's on the left side of the bowl, the force is pushing it back down. Always trying to get it where? Well, back here at equilibrium. In other words, where the potential is a minimum. The point where the potential is a minimum, that's where it's going to have a horizontal slope, in other words, a zero derivative, where the force is zero. So wherever we have a minimum in the potential, we're going to have zero force there. And when we displace the object one way or the other, the force always tries to restore the object back to equilibrium. We move it over to the right, the force pushes it to the left. We move the object to the left, the force pushes it to the right. This is what we call a restoring force. In other words, the force is always trying to restore the object to the F equals 0 point. Back, in this case, back in the, at the equilibrium. This is what we would call, when the force is 0, this is what we would call the object is in equilibrium. Whoops, sorry, missing some letters there. In equilibrium. And when we have a restoring force that always tries to bring it back to equilibrium, we call this a stable equilibrium. So the point where the force is 0, if the object were stationary there, not moving, 0 force means it's going to keep not moving. It's going to stay where it is. But if it's displaced a little bit and a restoring force tries to return it to equilibrium, that is what we call a stable equilibrium. Small displacements always bring the object back. On the other hand, imagine we had a potential that looked like a parabola upside down. In other words, like this. At this point up here, where the potential is a maximum, that is also a point where the force is 0. So if the object were sitting right on top of the potential, imagine like sitting on top of a very smooth bowl, that would be in equilibrium. It would also be in equilibrium. But what would happen if it was displaced a little bit? If this object moved over to the right, well then we have a force that keeps moving it to the right. If we were to move it to the left off equilibrium, the force would continue moving it to the left. This is not a stable equilibrium. This is called an unstable equilibrium. Any displacements from the equilibrium position would cause the object to continue to move away from the equilibrium point. This is not a restoring force. This is a very, very different kind of an equilibrium point. There's also another type of equilibrium, which is neither stable nor unstable. Imagine we had a potential with a very long, flat area to it. This could go like back down, this could go up or whatever. And the object were somewhere here. Again, there is no force. And if we were to displace the object, it's still at equilibrium, but there's no restoring force. There's no force trying to get it back to the original point. This type of equilibrium point is called a neutral equilibrium. A neutral equilibrium. Because there is no restoring force bringing it back to its original point, and there is no force trying to move it away from its original point. Neither one. So it's in equilibrium, but it's not stable or unstable. We say that it is a neutral equilibrium. Let's take a look at another potential that we'll see later on again when we start looking at gravitational forces, larger gravitational forces with, say, a planet around a star or something like that, or the moon around the Earth or something. Let's take a look at another potential.